imagine floating in space, far above the clouds, looking down at our small blue world. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From up there, Earth looks perfectly round, perfectly calm. But look a little closer. Our planet isn't standing straight up. It leans. It tilts to one side at an angle, like a spinning top that never quite found its balance. That lean, just 23.5 degrees off center, is the reason everything changes. It's the reason leaves turn gold in autumn. It's the reason snow falls in December and flowers push through cold soil in March. One small tilt, a world of difference. Earth travels around the sun in a great slow loop. That trip takes exactly 1 year to complete. As our planet moves through that loop, different parts of it face the sun more directly at different times. When the northern hemisphere tilts toward the sun, sunlight hits it at a steeper angle. The days grow long. The air grows warm. We call that summer. When the northern hemisphere tilts away, sunlight arrives at a shallow angle, spread thin across a wide area. The days shorten. The cold settles in. That is winter. The tilt never changes direction. Earth just moves around the sun, and the same lean that brought summer slowly brings winter in its turn. This is one of the most important things to understand about our seasons. They do not happen because Earth moves closer to the sun or farther away. In fact, Earth is actually slightly closer to the sun in January than in July. Distance is not the cause. The angle is everything. When sunlight hits the ground at a steep, direct angle, it concentrates its energy into a small area. That small area heats up quickly. When sunlight arrives at a low, glancing angle, that same energy spreads across a much larger patch of ground. The ground warms slowly, if at all. It's the same reason a flashlight aimed straight down makes a bright, tight circle, while a flashlight aimed sideways makes a wide, dim oval. Think about that for a moment. The same sun, the same light, the same planet, just a different angle. And from that single difference, every season blooms. The tilt also controls how long the sun stays in the sky each day. In summer, the sun rises early and and sets late. The sky holds its light for 16 hours or more in some places. In winter, the sun climbs low and slow, and it sets before the afternoon has barely begun. Some winter days in northern countries give only 7 or 8 hours of daylight. The length of the day shifts every single day of the year, creeping longer through spring, reaching its peak in June, then slowly pulling back through autumn toward the long, dark nights of December. This slow breathing of light and dark shapes almost everything on Earth's surface. Animals feel it in their bones. Plants read it in the sky. Whole ecosystems shift their rhythms to match the changing hours of sunlight. The tilt of our planet is not just a number in a textbook. It is the quiet engine running beneath every migration, every bloom, every harvest, every snowfall. Our planet has been leaning at roughly this same angle for billions of years. Scientists believe the tilt has shifted slightly over very long stretches of time. But for most of human history, that 23.5 degree lean has held steady. Ancient peoples noticed the patterns it created long before anyone understood the reason. They watched the sun rise and set at different points on the horizon through the year. They marked the longest day and the shortest day with stones and ceremonies. They built their lives around the rhythm the tilt created, even without knowing what caused it. There is something deeply calming about this. Our planet leans, and because it leans, the world turns through its seasons in a steady, reliable loop. Summer gives way to autumn. Autumn surrenders to winter. Winter slowly loosens its grip, and spring returns. Year after year, century after century, the same tilt, the same loop around the sun, the same beautiful cycle turning like a slow wheel. We live on a tilted world. We always have. And tonight, as you settle in and let your breathing slow, the planet beneath you is already leaning gently through space, carrying you along its ancient path around the sun, the same way it has carried every living thing that ever existed on this small, tilted, turning world. Earth doesn't stand up straight. It leans. Right now, as you lie here, our planet is tilted at an angle of about 23.5 degrees from perfectly upright. That lean is the reason you've ever felt a warm summer breeze or watched frost form on a window in the cold of January. Everything about the seasons starts with that single, quiet tilt. Picture a spinning top. When a top spins perfectly upright, it just spins in place. But when it leans a little to one side, something changes. The way it moves through space shifts. Earth is like that top. It spins on an invisible line called its axis, which runs straight through the planet from the North Pole to the South Pole. And that axis doesn't point straight up. It leans always in the same direction, like a tower that never quite stands vertical. That 23.5 degree tilt isn't random. Scientists believe it was set long ago, in the very early days of our solar system. About 4.5 billion years ago, the young Earth was struck by a large object, roughly the size of Mars. This collision was enormous. The impact was so powerful that it knocked a huge chunk of Earth's outer layer into space. That debris slowly gathered together and became the moon. And the force of that ancient crash also pushed Earth into its current lean. The moon we see glowing softly in the night sky is, in a way, a reminder of the same event that gave us our seasons. That tilt has stayed remarkably steady over millions of years. The moon itself helps keep it in place. The moon's gravity acts like a gentle hand on Earth's shoulder, holding the tilt stable so it doesn't wobble wildly. Without the moon, scientists believe Earth's tilt could swing dramatically over time, making the climate far more extreme and unpredictable. The moon isn't just a beautiful light in the night. It's a steady anchor for the conditions that allow life to thrive here. Now, here is where the tilt becomes something you can feel. As Earth travels around the sun each year, that 23.5 degree lean means different parts of the planet receive sunlight at different angles. When the northern hemisphere, the top half of Earth, tilts toward the sun, sunlight hits it more directly. More direct sunlight means more energy, more warmth. That is summer. 6 months later, when Earth has moved to the other side of its orbit, the northern hemisphere tilts away from the sun. Sunlight arrives at a shallower angle, spread out over a wider area, weaker and cooler. That is winter. Think of it this way. Imagine shining a flashlight straight down onto a table. The light makes a small, bright circle. Now tilt the flashlight at an angle. The same beam now spreads across a much larger oval. The light is the same, but it covers more ground, so any one spot gets less of it. That is exactly what happens to sunlight in winter. The sun's energy spreads thinner across the surface, and the days grow cold. The distance between Earth and the sun actually has very little to do with the seasons. This surprises many people. Earth is slightly closer to the sun in January than it is in July. In January, during the northern hemisphere's winter, Earth sits about 91 million miles from the sun. In July, during summer, it's about 94 million miles away. That small difference in distance barely changes the amount of heat we receive. The tilt is what matters. Angle, not distance, drives the seasons. The tilt also controls how long the sun stays in the sky each day. In summer, the tilted hemisphere faces the sun for more hours. Days stretch long and golden. In winter, that same hemisphere faces away, and the sun rises late and sets early, leaving long, dark nights. The length of daylight and the angle of sunlight work together, layering their effects on top of each other. Summer days are warm not just because the sunlight is stronger, but because there are more hours of it. All of this flows from one ancient collision, one 23.5-degree lean, one invisible axis running through the heart of our planet. It is a system built from violence and chance, and yet it runs with quiet precision. The tilt doesn't change from day to day. It holds steady year after year, guiding the seasons in their slow, reliable rhythm. Spring follows winter. Summer follows spring. The same tilt that was set billions of years ago is the reason leaves are falling somewhere on Earth right now, and flowers are blooming somewhere else at the very same moment. Picture the young Earth spinning in the dark. It's a violent, restless world. Oceans of molten rock glow red across its surface. The sky is thick with ash and gas. There are no seasons yet. There is no tilt. The young Earth spins nearly straight up, like a top that hasn't wobbled yet. Then something hits it. Scientists call it Theia, a planet roughly the size of Mars. It crashes into the early Earth about 4.5 billion years ago at an angle with tremendous force. The collision is so powerful that it melts both worlds together. Rock and metal and fire spray out into space in a vast, glowing cloud. That cloud slowly pulls itself together under its own gravity and forms the moon. But the crash does something else too. It knocks Earth off its straight, upright spin. It tilts our planet, and that tilt, that small, quiet lean of about 23.5 degrees, is the reason we have seasons at all. Think about what that means. Every spring morning you've ever felt, every summer afternoon, every autumn evening when the light turns gold and low, every winter night that comes too early, all of it traces back to one ancient collision, one moment of cosmic violence billions of years ago gave our world its rhythm. Now, the tilt itself doesn't change much. Earth holds that 23.5 degree lean with remarkable steadiness as it travels around the sun. What changes is which part of Earth is leaning toward the sun and which part is leaning away. That shift is what drives the dance of sunlight across the seasons. Here's how it works. Earth takes about 365 days to complete one full trip around the sun. As it moves through that orbit, the tilt stays pointed in the same direction in space, toward a distant star called Polaris, the North Star. So for 1/2 of the year, the northern hemisphere leans toward the sun. For the other half, it leans away. That leaning changes everything about how sunlight reaches the ground. When the northern hemisphere leans toward the sun, sunlight hits at a steeper, more direct angle. Think of shining a flashlight straight down onto a table. The light makes a small, bright circle. That concentrated light carries more energy. It warms a smaller patch of ground much more intensely. That's summer. The days grow long. The sun climbs high in the sky. The warmth builds. When the northern hemisphere leans away from the sun, that same sunlight arrives at a shallower angle. Now, the flashlight is tilted, and the circle of light stretches into a wide, dim oval. The same amount of energy spreads across a much larger area of ground. Each patch of Earth receives less warmth. The days shorten. The sun stays low. That's winter. it's not about distance. This surprises many people. Earth is actually slightly closer to the sun in January than in July. But closeness matters far less than angle. A direct beam warms. A glancing beam barely touches. The tilt controls the angle, and the angle controls the heat. The southern hemisphere experiences all of this in reverse. When the north leans toward the sun and enjoys summer, the south leans away and settles into winter. They trade places every 6 months, perfectly out of step with each other, like two dancers moving in opposite directions around the same slow circle. The length of the day changes too, and this is just as important as the angle of sunlight. When a hemisphere leans toward the sun, it spends more of Earth's daily rotation facing the light. Days stretch long. The sun rises early and sets late. All those extra hours of daylight add up to enormous amounts of heat absorbed by the land and sea. When a hemisphere leans away, the days shrink. The sun rises late and sets early. The ground loses more heat to the cold night than it gains from the short day. These two effects, the angle of sunlight and the length of the day, work together. They reinforce each other. In summer, you get both more intense light and more hours of it. In winter, you get both weaker light and fewer hours. The two forces push in the same direction, which is why the difference between seasons can feel so dramatic. Even though Earth's tilt never changes. All of this began with a collision. A wandering planet struck a young world at just the right angle, at just the right speed, and left behind a lean that would shape every living thing that ever grew on this planet. The tilt was born in fire. The seasons grew from it slowly, quietly, over billions of years. Summer arrives slowly. You don't always notice it coming. But one morning, the light is different, brighter, earlier, staying longer than it did the week before. The air holds more warmth. The shadows grow shorter. And all of it traces back to one simple thing: the angle at which sunlight strikes the ground. When Earth's northern hemisphere tilts toward the sun, sunlight doesn't just arrive earlier and leave later. It arrives more directly. Think of shining a flashlight straight down onto a table. The light makes a tight, bright circle. Now tilt that flashlight at an angle. The same beam spreads across a wider area, and each part of that area gets less light, less heat. In summer, the sun shines more like that first flashlight, straight down, concentrated, intense. This is why summer days feel so different from winter ones. It isn't just the extra hours of light, it's the quality of that light. Summer sunlight travels a shorter path through the atmosphere, that thin shell of air wrapped around Earth before it reaches the ground. Less atmosphere means less scattering. Less scattering means more energy arrives at the surface. The ground absorbs it. The air above it warms. And slowly, steadily, summer builds. That warmth doesn't appear from nowhere. It comes from the sun, which has been burning for about 4.6 billion years. At its core, hydrogen atoms are crushed together under enormous pressure and fuse into helium. This process, called nuclear fusion, releases staggering amounts of energy. A tiny fraction of that energy travels 93 million miles across empty space and lands on your skin on a summer afternoon. What feels like simple warmth is actually ancient stellar fire crossing the void to reach you. The light itself is made of photons, tiny packets of energy that have no mass and travel at the speed of light. They leave the sun's surface and cross the solar system in about 8 minutes. When they strike Earth's surface in summer, they carry more energy per square foot than at any other time of year. The ground absorbs this energy and re-releases it as heat. Dark surfaces like soil and rock absorb more. Lighter surfaces like sand and snow reflect more back into the sky. This difference shapes entire climates. Summer days grow long because of Earth's tilt working together with its orbit. Near the summer solstice, the single day each year when the northern hemisphere tilts most directly toward the sun. Some places near the Arctic Circle receive sunlight for nearly 24 hours straight. The sun dips low toward the horizon at midnight, but never quite disappears. This is called the midnight sun, and it has stunned travelers and explorers for centuries. The sky glows a deep amber gold, and the world feels suspended between day and night. Even the color of summer light tells a story. When the sun is high overhead, its light passes through less atmosphere, so it appears white and sharp. When it sits low on the horizon at dawn or dusk, that same light travels through much more air. The shorter wavelengths of light, the blues and violets, scatter away. Only the longer wavelengths survive the journey. Reds, oranges, the warm gold of a summer evening. The colors of sunrise and sunset are written in the physics of how light moves through air. All of this heat, this light, this long golden day, it doesn't stay in one place. The atmosphere carries it. Ocean currents move it. Warm air rises from heated land and travels toward the poles. Cooler air rushes in to replace it. This constant movement of air and heat is what we call weather, and summer drives it with particular force. Thunderstorms build in the afternoon heat. Winds shift. Rain falls. The energy the sun pours into the ground in summer gets redistributed across the whole planet, feeding storms and breezes and the slow circulation of the seas. The ground itself stores summer's heat. Soil and rock absorb warmth during the long days and release it slowly at night. This is why the hottest part of summer often comes weeks after the longest day. The land is still releasing heat it collected earlier. Scientists call this effect the lag of the seasons, and it explains why July and August feel hotter than June in the northern hemisphere, even though the days are already getting shorter by then. Summer, then, is not just a season. It's a chain of causes and effects. A tilt leads to an angle. An angle concentrates light. Light becomes heat. Heat moves through air and water and stone. And the whole living world responds, reaching upward, opening outward, drawing in as much energy as it can before the tilt begins to shift again. Winter arrives without announcement. One morning, the light looks different. The shadows stretch longer. The air holds a chill that wasn't there before. Something has quietly shifted, and the forces behind that shift have been at work for billions of years. The most important force in winter is distance. Not distance from the sun. That's a common mistake. Earth is actually slightly closer to the sun in January than in July. The real distance that matters is the angle. Because Earth tilts at about 23.5 degrees, the northern hemisphere leans away from the sun during winter months. Sunlight still arrives, but it arrives at a low, slanted angle, spread across a much wider area of ground. Think of it this way. Imagine shining a flashlight straight down onto a table. The light makes a small, bright circle. Now tilt that flashlight sideways. The same beam of light spreads into a long, dim oval. The energy hasn't changed, but it's covering more ground, so each patch of ground gets less warmth. That's exactly what happens to winter sunlight. The same solar energy spreads thin across the land, and the ground cools. This spreading of sunlight is called the angle of incidence, the angle at which light strikes a surface. In winter, that angle is low and shallow. The sunlight travels through more of Earth's atmosphere before it reaches the ground. The atmosphere absorbs and scatters some of that energy along the way. So winter light is not only spread wider, it's also filtered more. Less heat reaches the surface. The land, the water, and the air all begin to cool. The cooling doesn't happen all at once. Earth's surface holds heat the way a thick stone wall holds warmth after a fire. The oceans especially hold onto summer's energy for weeks. This is why the coldest months of winter often come in January and February, long after the shortest day has already passed in December. The ground and water are slowly releasing the last of their stored warmth, like embers fading in the dark. As the land cools, the air above it cools too. Cold air is denser and heavier than warm air. It sinks. It spreads outward across the surface. This is how winter builds its pressure systems. Vast, heavy domes of cold air that settle over the land and push milder air aside. These high-pressure systems bring clear skies and biting cold. They are not violent. They are patient. They simply press down, slow and steady, and the world beneath them goes quiet. Water plays a powerful role in all of this. When temperatures drop far enough, water changes form. Liquid water in lakes and rivers begins to freeze. Snow falls and covers the ground in a white blanket. And here is something remarkable. Snow reflects sunlight. A fresh snowfield can reflect up to 90% of the sunlight that hits it. Scientists call this reflectivity albedo. High albedo means more sunlight bounces back into space instead of warming the ground. So snow doesn't just result from cold, it helps create more cold. Winter feeds itself. The tilt of Earth also controls how many hours of daylight a place receives. In winter, the northern hemisphere tilts away from the sun. The sun rises later and sets earlier. Days grow short. In some northern cities, the sun is above the horizon for only 7 or 8 hours. That's 7 or 8 hours for the ground to absorb any warmth at all. The long nights give the land many more hours to radiate heat back into the sky. The cold deepens simply because darkness lasts so long. Far to the north, above the Arctic Circle, the sun doesn't rise at all for weeks at a time. This is called polar night. The land sits in complete darkness, losing heat steadily with nothing to replace it. Temperatures can fall to extraordinary lows. The atmosphere itself becomes still and glassy. The sky sometimes fills with curtains of green and violet light, the aurora borealis, caused by charged particles from the sun colliding with gases high in the atmosphere. Even in the deepest withdrawal of winter, the sun is still reaching out. And that is the quiet truth of winter. It is not an absence of the sun. It is a turning away. Earth's tilt carries the northern hemisphere into shadow, and the forces of angle, atmosphere, reflection, and long dark nights all work together to pull the warmth from the land. Slowly, steadily, the world cools and rests. The soil hardens. The trees stand bare. And somewhere already, the tilt is beginning its long return. Winter is not an ending. It is a pause before the next turning. Spring begins quietly. There is no sharp edge to it, no single moment when winter ends and warmth begins. It arrives the way light fills a room at dawn, so slowly you almost miss it happening. After the long withdrawal of winter, Earth's tilt begins to shift the northern hemisphere back toward the sun. Each day, the sun climbs a little higher in the sky. Each day, it stays up a little longer. The change is small at first, just a few extra minutes of daylight every week. But those minutes add up, and the world begins to stir. To understand how much that extra light matters, think about this. In the depths of winter. A city like New York receives only about 9 hours of sunlight each day. By late spring, that same city receives nearly 15 hours. That is 6 full hours of extra solar energy pouring onto the ground, the trees, the rivers, and the soil every single day. 6 hours of warmth that was simply absent just a few months before. That extra light carries real power. The sun delivers roughly 1 kilowatt of energy to every square meter of Earth's surface on a clear day. 1 kilowatt is enough to run a microwave oven. Now imagine that energy falling across millions of square kilometers of land and ocean, hour after hour, day after day, for an entire season. The scale of it is almost too large to picture. Spring is not a gentle nudge. It is an enormous, slow flood of energy reshaping the surface of an entire hemisphere. The soil feels it first. Frozen ground begins to thaw from the surface downward. In places like northern Canada or Siberia, the ground can freeze to depths of several meters during winter. As spring arrives, that thaw moves downward at roughly a centimeter or 2 per day. It takes weeks, sometimes months, for the warmth to reach the deeper layers. The ground does not simply wake up all at once. It warms in stages, like a thick blanket slowly absorbing heat from one side. Snowpack tells a similar story. The mountain snowfields that built up all winter begin to melt. In the American West, the Sierra Nevada mountain range holds billions of gallons of water locked in snow each winter. When spring arrives and that snow melts, it feeds rivers and reservoirs that supply drinking water to tens of millions of people. The tilt of Earth, 23.5 degrees off vertical, is the reason that water exists at all. Without the tilt, there would be no winter snowpack. Without the snowpack, those rivers would run thin and dry. Temperature changes in spring can feel dramatic, but the actual numbers are surprisingly modest. In many temperate regions, places with 4 distinct seasons, like Central Europe or the American Midwest, average temperatures rise by only about 1 degree Celsius per week through early spring. 1 degree. That is barely enough to feel on your skin. Yet that single degree, repeated week after week, is enough to coax seeds out of frozen ground, pull migrating birds thousands of kilometers northward, and trigger the flowering of millions of plants. The reason small changes produce such large effects comes down to thresholds. Many living things are tuned to respond to very precise temperature triggers. Cherry trees, for example, begin to bloom when average temperatures consistently reach around 7 degrees Celsius. Below that, nothing happens. Above it, the tree bursts into flower within days. The difference between a bare branch and a cloud of pink blossoms is sometimes just 1 or 2 degrees of warmth. Earth's tilt delivers exactly that margin, right on schedule, year after year. Daylight drives this process just as powerfully as warmth. Plants measure the length of the day with remarkable precision. Some species will not flower until the day reaches a specific number of hours of light, not approximately, but exactly. Scientists call this response photoperiodism, which means the ability of a plant or animal to sense and respond to the length of daylight. Earth's tilt controls the length of every day of the year. In that sense, the tilt is not just a physical fact about our planet's angle in space. It is a clock, a calendar, a signal that the entire living world reads and responds to. Spring's awakening looks gentle from the outside. Soft green shoots pushing through brown soil. A robin pulling a worm from damp earth. The pale yellow of early daffodils against a gray sky. But underneath that quiet surface, enormous forces are at work. Billions of tons of snow melting. Trillions of seeds responding to light. An entire hemisphere tilting degree by degree back into the warmth of the sun. It happens every year. It has happened for billions of years, and it will keep happening quietly and reliably for billions more. Somewhere in the middle of the year, the light begins to change. It happens slowly, almost too slowly to notice at first. The sun sits a little lower in the sky each afternoon. The shadows grow a little longer, and the world, almost without a sound, begins to let go. This is autumn, and it is one of the most beautiful things our tilted planet does. As Earth continues its path around the sun, the northern hemisphere starts to lean away from the light. not dramatically, not all at once, just a quiet, steady withdrawal a few degrees at a time. The angle of sunlight grows shallower, the days shorten, and the surface of the earth begins to cool. Stand in a forest in October, somewhere in the northeastern United States or across Central Europe, and look up. The canopy above you is on fire, not with heat, but with color, reds and oranges, and deep burning yellows, all pressed together overhead like stained glass lit from behind. The light that filters through is warm and golden, the kind of light that feels like it's saying goodbye. Those colors were always there, hidden beneath the green. Leaves get their green color from chlorophyll, the chemical that helps them turn sunlight into food. As the days grow shorter and the light grows weaker, trees stop making chlorophyll. The green fades, and the other colors, the reds and yellows and oranges that were always present in the leaf, finally show through. Autumn doesn't paint the trees. It simply reveals what was already there. The red colors are a little different. Many trees actually produce new red pigments in autumn, called anthocyanins. Scientists believe these pigments may help protect the leaf during its final weeks, acting like a kind of sunscreen as the tree pulls nutrients back from the leaf before dropping it. The tree is not wasting those leaves. It's harvesting them, pulling sugars and minerals back into its branches and roots before the cold arrives. The falling leaf is the last act of a very careful process. Walk through those fallen leaves and you hear them. That dry, papery crunch underfoot is the sound of autumn made physical. The leaves have lost almost all their moisture. They've become light and brittle, curling at the edges, their surfaces rough and papery to the touch. Some are still bright. Others have faded to brown, their colors spent. They gather in drifts along fences and at the base of trees, slowly beginning to break down, slowly beginning to return to the soil. That process matters more than it might seem. Fallen leaves become food for fungi and bacteria and tiny insects that live in the top layer of soil. Those organisms break the leaves down into rich, dark material called humus, which feeds the roots of the very trees that dropped the leaves in the first place. The forest floor in autumn is not a graveyard. It is a kitchen quietly preparing the next season's meal. Look up from the forest floor, and the sky in autumn has its own particular quality. The air is drier than summer's thick, humid warmth. The sky goes a deeper shade of blue. Clouds move faster, pushed by winds that are picking up as the temperature difference between the equator and the poles begins to grow. That growing difference in temperature is what drives autumn's weather. Cold air pushing down from the north, warm air retreating south, and the boundary between them churning into storms and wind and the first cold rains. Frost comes to the low places first. On a still, clear autumn night, heat rises from the ground and escapes into the sky. Without cloud cover to hold it in, the ground cools quickly. Water vapor in the air near the surface freezes into tiny crystals on grass and leaves and car rooftops. By morning, the world has a thin white coating, delicate as powdered sugar. Gone by mid-morning, once the sun climbs high enough to melt it. The fields in autumn have their own look. Harvested rows of corn or wheat leave behind pale stubble, stretching in long lines across the brown earth. Pumpkins sit heavy and orange in the dirt. The soil itself looks darker after the first rains, rich and dense, ready to rest through the cold months ahead. Autumn is the season of release. The trees release their leaves. The fields release their harvest. The days release their light a little earlier each evening. Everything is preparing, quietly and without hurry, for the stillness that winter brings. And all of it, every falling leaf and lengthening shadow, is the work of a single, steady tilt, carrying our world gently around the sun. Twice a year, something quiet and precise happens in the sky. The sun rises exactly due east. It sets exactly due west. And for one single day, the light and the dark divide the world into two equal halves. This is the equinox. The word comes from Latin. Equus means equal. Nox means night. Equal night. On these 2 days, every place on Earth receives almost exactly 12 hours of daylight and 12 hours of darkness. From the frozen tundra of northern Canada to the warm coasts of Brazil, the split is nearly the same. It happens because of the tilt. Earth leans at about 23.5 degrees as it circles the sun. For most of the year, that tilt points one hemisphere toward the sun and the other away. But twice a year, Earth reaches a position in its orbit where neither hemisphere leans toward or away. The planet stands, in a sense, sideways to the sun. The sun's light falls directly on the equator, that invisible line circling Earth's middle, and the whole world shares the light almost evenly. There are 2 equinoxes every year. The March equinox arrives around the 20th or 21st of that month. The September equinox follows about 6 months later, around the 22nd or 23rd. In the northern hemisphere, the March equinox marks the start of spring. The September equinox marks the start of autumn. In the southern hemisphere, those seasons are reversed. March brings autumn there. September brings spring. The equinox is not just a moment in a calendar. It is a physical event. On that day, if you stood at the equator and looked straight up at noon, the sun would be directly overhead, not slightly to the north, not slightly to the south, directly above you, blazing straight down. A vertical stick pushed into the ground would cast almost no shadow at all. The light falls perfectly plumb. Scientists call this the subsolar point, the exact spot on Earth's surface where the sun sits directly overhead. On the equinox, that point rests right on the equator. Every other day of the year, it drifts either north or south, following the tilt. But on these 2 days, it returns to center. There is something almost mathematical about it. The sun crosses what astronomers call the celestial equator, an imaginary line projected outward from Earth's own equator into space. When the sun crosses that line heading north, it is the March equinox. When it crosses heading south, it is the September equinox. The sky itself has a kind of geometry, and twice a year, Earth passes through its most balanced point. The word almost matters here. Most people expect the equinox to deliver a perfect 12-hour day. But the actual length of daylight on equinox day is slightly more than 12 hours in most places. This happens for 2 reasons. First, the sun is not a single point of light. It is a disk, and sunrise is counted from the moment the top edge of that disk appears above the horizon, not the center. few extra minutes of light. Second, Earth's atmosphere bends sunlight, a process called refraction, which causes the sun to appear above the horizon even when it is technically still just below it. Together, these two effects give most locations a day that runs a few minutes longer than a perfect half-and-half split. The equinox also marks a turning point in how quickly the days are changing. Around the solstices, the longest and shortest days of the year, the amount of daylight barely shifts from one day to the next. But near the equinoxes, the change is fastest. In the days surrounding the March and September equinoxes, the length of daylight can shift by 2 to 3 minutes every single day. The world is moving through its most rapid transition. The light is either rushing in or rushing away, faster than at any other time of year. Ancient peoples felt this. They built monuments to mark it. Stonehenge in England aligns with the equinox sunrise. The Great Pyramid of Kukulkan in Mexico, built by the Maya, casts a shadow on the equinox that looks like a serpent descending its steps. These were not accidents. They were careful observations built in stone so that the turning of the year could never be forgotten. The equinox is a hinge, a moment of balance between two long swings. The world tips one way, then the other, and twice a year it passes through the still point in between. Not quite equal, but closer to equal than any other day. A brief, precise pause in the slow lean of a tilted world. Twice a year, the Earth reaches a moment unlike any other. The tilt of our planet lines up with the sun in the most extreme way possible. One hemisphere leans as far toward the sun as it ever will. The other leans as far away. These moments are called solstices, and they mark the turning points of the year. The word solstice comes from Latin. It means sun stands still. And in a way, that is exactly what happens. For a few days around each solstice, the sun rises and sets at nearly the same point on the horizon. It seems to pause. Then, slowly, it begins to drift back the other way. Ancient people noticed this. They watched the sky carefully, and they knew that when the sun stopped moving, the season was about to turn. The June solstice arrives around the 21st of every June. On this day, the the northern hemisphere tilts its maximum 23.5 degrees toward the sun. The sun climbs higher in the sky than on any other day of the year. It stays above the horizon longer than any other day. In the far north, places like Norway and Iceland see the sun for 24 hours straight. The sky never fully darkens. A soft, golden light lingers all through the night. This is the summer solstice for the northern hemisphere. It is the longest day of the year. The sun reaches its highest point in the sky at noon, casting the shortest shadows you will see all year. Stand outside at midday, and your shadow barely stretches past your feet. The sun is almost directly overhead, pouring its energy straight down onto the land. At the same moment, the southern hemisphere is tilted away. There, it is the winter solstice, the shortest day of the year. The sun rises late and sets early, tracing a low, shallow arc across the pale sky. In parts of Antarctica, the sun does not rise at all. The continent sits in continuous darkness, cold and still, waiting for the slow return of light. Then the cycle continues. The Earth keeps moving along its orbit. The tilt stays the same, but the position of Earth relative to the sun changes. The northern hemisphere begins to lean away. The days grow shorter. The sun drops a little lower each noon. The shadows stretch a little longer each day. By December, the cycle reaches its other extreme. The December solstice arrives around the 21st of December. Now, the southern hemisphere tilts its full 23.5 degrees toward the sun. It is summer in the south. Long days, high sun, short shadows. Meanwhile, the northern hemisphere leans away into its deepest winter. Days are short. The sun skims low across the horizon, barely climbing before it begins to sink again. At the North Pole, on the December solstice, the sun has not risen in months. The polar night, called polar darkness, has settled in. The sky is black for weeks at a time. Only the stars and the moon, and sometimes the shimmering green curtains of the aurora borealis, light the ice below. What makes the solstice so remarkable is not just the extreme light or darkness. It is what comes after. The solstice is a turning point, a hinge in the year. After the June solstice, the days in the northern hemisphere begin to shorten. Slowly at first, just a minute or two each day, then faster. The change is barely noticeable at first, but it is happening. The sun is retreating. The season is already beginning its quiet turn toward autumn. After the December solstice, the opposite begins. The days in the northern hemisphere start to lengthen. 1 minute, then 2, then 5. The sun climbs a little higher each week. The light is returning. Even in the coldest, darkest weeks of January and February, the days are already growing longer. The solstice has already passed. The wheel has already turned. This rhythm is ancient. It has been turning since long before there were humans to watch it. The Earth has been leaning and orbiting, cycling through its solstices for billions of years. Every living thing on this planet has evolved inside that rhythm. Plants know it. Animals know it. Even the oceans feel it, warming and cooling in response to the sun's changing angle. The solstice is not just a date on a calendar. It is a pulse, a steady, reliable beat that the Earth has kept for longer than we can truly imagine. And twice a year, right on schedule, the sun reaches its farthest point, pauses for just a breath, and then begins its slow return. There are places on this earth where the sun does not set for months. And then, just as slowly, it does not rise for months. These are the poles, and the seasons they experience are unlike anything most of us will ever see. At the North Pole and the South Pole, Earth's tilt does something extraordinary. Because our planet leans at that steady 23.5 degrees, the poles spend half the year tilted toward the sun and half the year tilted away. This creates seasons that are not measured in warmth or cold alone. They are measured in light and darkness. During the Arctic summer, the sun circles the sky without ever dipping below the horizon. It traces a wide, low loop overhead, hour after hour, day after day. This is called the midnight sun. For weeks, sometimes months, the sky stays bright even at midnight. The light is soft and golden, never quite overhead, always slanting in from the side like a long afternoon that never ends. In the high Arctic, this continuous daylight can last for up to 6 months near the pole itself. Then the season turns, the tilt shifts, and the sun begins to sink lower with each passing day, until one morning it does not rise at all. This is called polar night. The sky stays dark, or lit only by stars and the faint glow of the moon, for weeks at a stretch. Near the pole, polar night can last as long as the midnight sun. 6 months of light, then 6 months of darkness. The year divides itself in two. This is not the same as the seasons people experience in the middle latitudes, where temperature drives the change. At the poles, the defining force is light. The sun's angle is so low that even during summer, its rays spread across a wide area rather than concentrating their heat. This is why the poles stay cold even in their brightest months. The light arrives, but it arrives gently, spread thin across the ice. The Arctic and Antarctic do not experience seasons in perfect mirror image, though. The South Pole sits on a continent, Antarctica, a vast frozen landmass buried under ice more than a mile thick in places. The North Pole sits on the Arctic Ocean, covered by floating sea ice. Land holds cold differently than water does. Antarctica stays colder longer, more deeply frozen. The Arctic is more responsive to change. These two poles share the same tilt, the same cycle of light and dark, but their surroundings shape their seasons in very different ways. The edges of the polar regions, the areas just outside the Arctic and Antarctic circles, experience something in between. They have long summer days and long winter nights, but not the full continuous light or full continuous dark of the poles themselves. The Arctic Circle sits at about 66.5 degrees north latitude. Cross that invisible line, and you enter a world where at least one day a year the sun never fully sets, and at least one day it never fully rises. The further north or south you travel from there, the more extreme the contrast becomes. Life at the poles has learned to read these rhythms with extraordinary precision. The Arctic tern, a small seabird, migrates from the Arctic to the Antarctic and back again every year. It follows the summer from pole to pole, chasing the long days across the entire length of the planet. Scientists believe it experiences more daylight each year than any other creature on Earth. It lives inside the light, following it endlessly around the globe. The polar seas respond to the seasons too. In Arctic summer, sea ice melts back and the ocean opens up. Cold, nutrient-rich water rises to the surface. Tiny plants called phytoplankton bloom in enormous numbers, turning the water green and blue-green. These blooms feed everything from small shrimp-like creatures called krill to whales. The whole food chain wakes up with the returning light. Then winter comes. The ice spreads back across the ocean, and the sea quiets again. What happens at the poles does not stay at the poles. The cold air that builds over Antarctica in winter spills outward, driving wind patterns that circle the entire southern hemisphere. The Arctic sea ice reflects sunlight back into space, helping to regulate the temperature of the whole planet. These distant, frozen places are not separate from the world most of us live in. They are part of the same great turning system, connected by wind and water, and the slow, steady tilt of this planet as it moves around the sun. The poles are the farthest reaches of Earth's seasonal swing, and they remind us how wide and strange and generous this tilted world truly is. Watch the sun tomorrow. Step outside in the morning and notice where it rises. Then check again at noon. Then once more before it sets. You'll see something that humans have watched for thousands of years. The sun doesn't just move across the sky, it traces an arc. And that arc changes every single day of the year. In summer, the sun climbs high. It swings wide across the sky in a long, sweeping curve. At noon in midsummer, the sun sits almost directly overhead for people living in the middle latitudes. Places like the American Midwest, Southern Europe, or Central China. The light falls nearly straight down. Shadows shrink to almost nothing beneath your feet. The sun's energy hits the ground at a steep angle, and that steep angle is what makes summer so warm. In winter, everything shifts. The sun rises lower on the horizon. It never climbs very high, even at noon. It traces a short, shallow arc across the sky, staying close to the south, or close to the north if you live in the southern hemisphere. The light hits the ground at a slant, spreading out over a wider area. That spread is why winter light feels so thin and pale. The same amount of energy from the sun covers more ground, so each patch of ground gets less warmth. The difference in the sun's height between summer and winter is called the solar elevation angle. At the summer solstice in New York City, the sun reaches about 73 degrees above the horizon at noon. At the winter solstice, that same noon sun sits only about 26 degrees above the horizon. That's a swing of nearly 47 degrees, almost half the distance between the horizon and the point directly overhead. The same sun, the same city, but the sky it travels through looks completely different depending on the time of year. Near the equator, this change is small. The sun stays fairly high all year long. Seasons near the equator are mild, driven more by rain and dry spells than by temperature swings. But the farther you travel from the equator, the more dramatic the sun's arc becomes. At the Arctic Circle, the summer sun barely sets at all, grazing the horizon at midnight before climbing again. In winter, it barely rises. The arc shrinks to almost nothing, a shallow dip above the horizon for just a few hours before vanishing again. The most extreme version of this happens at the poles. At the North Pole on the summer solstice, the sun circles the sky at a constant low angle, never rising high, never setting. It just moves in a flat ring around the horizon, all day, all night. For 6 full months, the sun never disappears. Then, at the winter solstice, the opposite is true. The sun never rises at all. The sky stays dark for months. The pole swings between total light and total darkness, and nothing in between. There's a moment each year when the sun reaches its highest point in the sky for that entire year. That moment is called solar noon at the solstice. And for people in the northern hemisphere, it happens around June 21st. On that day, if you stand at the Tropic of Cancer, a line that runs through Mexico, the Sahara Desert, and southern India, the sun passes directly overhead at noon. Your shadow disappears completely beneath you. The sun is exactly 90 degrees above the horizon. It's the highest the sun ever gets for anyone living north of the equator. 6 months later, the sun reaches its lowest noon position of the year. On the December solstice, the sun is at its farthest southern point. People in the southern hemisphere now experience their highest sun, their longest day. The Tropic of Capricorn, running through Brazil, southern Africa, and Australia, becomes the place where the sun stands directly overhead. The planet has simply tilted the other way. All of this happens because of that 23.5-degree lean. That single tilt is the reason the sun's arc shifts across the sky with every passing week. It's the reason shadows are long in December and short in June. It's the reason a winter afternoon feels like dusk, even at 3 o'clock. The sun hasn't moved closer or farther. It hasn't changed. Only the angle has changed. And that angle controls everything: the warmth of the air, the length of the day, the color of the light, the feel of the season on your skin. The sky is the same sky. The sun is the same sun. But the tilt of this small, spinning world makes it look completely different depending on where you stand and when you look up. Something shifts in the animal world long before the first frost appears. The air might still feel warm. The leaves might still be green. But deep inside the bodies of birds, bears, and butterflies, a quiet signal has already arrived. The seasons speak to animals in a language older than any human word. That language is light. The amount of daylight in a single day changes slowly as Earth tilts through its orbit. Animals feel this change with remarkable precision. Many creatures have special cells inside their eyes and even inside their brains that measure the exact length of each day. These cells don't just register brightness. They count hours, and when the hours of light begin to shrink, the body listens. Deer are a beautiful example of this. As the days grow shorter in late summer, a deer's brain sends a signal to its body to begin growing a thick winter coat. The deer doesn't feel cold yet. It doesn't need to. The shrinking daylight is warning enough. By the time the cold actually arrives, the deer is already dressed for it. The body prepares weeks ahead of the season's arrival, trusting the light more than the temperature. Birds feel the shift too, but they respond in a different way. many species begin storing extra fat in their bodies as the days shorten. This fat becomes fuel for long migrations, those incredible journeys of thousands of miles that some birds make every single year. The Arctic tern, a small seabird, travels from the Arctic to Antarctica and back again each year. That's roughly 44,000 miles in a single round trip. The trigger for all that movement is not hunger, not cold. It's the slow, steady change in the length of the day. Some animals go even further. They don't migrate. They disappear. Bears enter a state called torpor, a deep, slow rest where the heart rate drops and the body burns stored fat instead of food. A black bear's heart can slow from about 55 beats per minute down to just 8 beats per minute during this rest. The bear breathes just a few times a minute. Its body temperature drops only slightly, which is different from true hibernation, where the temperature falls much more sharply, but the effect is the same. The bear becomes almost still, tucked into a den, waiting for spring. What triggers this? Again, the light. The shortening days of autumn signal the bear's body to eat more, store fat, and prepare for the long quiet. The bear doesn't decide to hibernate. Its body decides for it, guided by the same ancient clock that guides the deer and the tern. Smaller creatures feel the shift too, in their own quiet ways. Honeybees stop leaving the hive as the days grow short. They cluster together in a tight ball at the center of the hive, shivering their wing muscles to generate heat. The queen stops laying eggs. The whole colony turns inward, surviving on stored honey through the cold months. When the days lengthen again in late winter, the queen begins to lay once more, even before the first flowers appear outside. Some insects take an even more dramatic step. The monarch butterfly, that small orange and black creature, migrates from Canada and the northern United States all the way to a small cluster of forests in central Mexico. Millions of monarchs gather in those trees, covering the branches so thickly that the trees seem to glow orange. Scientists believe the monarchs navigate using a combination of the sun's position and an internal clock that tracks the time of day. The changing angle of sunlight in late summer tells them it's time to move. Even fish respond to the seasons. Salmon use changes in water temperature and day length to time their upstream migration. Their bodies begin to change months before they reach their spawning grounds, the shallow streams where they were born. The shift in light sets off a cascade of changes inside them, reshaping their bodies for the enormous effort ahead. All of these animals are reading the same slow signal. They're measuring the same tilted earth, the same shifting angle of sunlight, the same gradual shortening and lengthening of days. They don't know about orbits or axial tilt. They don't need to. Their bodies have been tuned to Earth's rhythm over millions of years, shaped by the same forces that tilt our planet and carry it around the sun. There is something deeply calming about this. Every creature, from the great bear to the small honeybee, is held inside the same slow turning of the year. Each one resting, moving, or waking exactly when the light tells it to. Plants don't have eyes. They can't look up at the sky and watch the sun climb higher each morning. They can't feel a calendar page turn. And yet, somehow, a cherry tree knows exactly when to bloom. A maple knows when to let its leaves go. A sunflower knows which direction to face and when to stop growing. For thousands of years, people watched this happen and wondered how. The answer took a long time to find, and the story of how humans figured it out is quiet and patient, much like the plants themselves. Early farmers noticed the connection between seasons and plant behavior long before anyone understood the science behind it. They kept records. They watched. They planted by the stars and by the length of the day. Ancient Egyptian farmers tracked the flooding of the Nile and the movement of certain stars to know when to sow their crops. Ancient Chinese farmers wrote detailed notes about which plants bloomed at which time of year. These weren't guesses. They were careful observations passed down across generations. But the real question, the one that took centuries to answer, was this: what exactly were the plants responding to? Was it temperature, rainfall, something else entirely? For a long time, most people assumed plants woke up in spring because of warmth. It made sense. The air gets warmer, the ground thaws, and the flowers appear. Temperature seemed like the obvious trigger, and temperature does matter. But it isn't the whole story. In the early 1900s, two American scientists named Whitman Garner and Henry Allard were studying tobacco plants at a research station in Maryland. They noticed something strange. A particular variety of tobacco plant, called Maryland mammoth, kept growing and growing through the summer without ever flowering. It only bloomed in winter when they moved it inside a greenhouse. This made no sense to them. The temperature inside the greenhouse wasn't dramatically different. So, what was causing the change? Garner and Allard ran careful experiments. They grew plants in controlled conditions, changing one variable at a time. They adjusted temperature. They adjusted water. They adjusted light. And then they found it. The plants weren't responding to warmth. They were responding to the length of the day, specifically to the number of hours of darkness in each 24-hour period. They called this phenomenon photoperiodism, which means the response of a living thing to the length of light and dark in a day. They published their findings in 1920, and it changed the way scientists understood plant life forever. What Garner and Allard had discovered was that plants are, in a very real sense, reading the tilt of the earth, because the tilt is what causes day length to change across the seasons. In summer, days are long and nights are short. In winter, nights stretch out and days shrink. A plant measuring the hours of darkness is, without knowing it, measuring where Earth sits in its orbit around the sun. Some plants flower only when nights are long, meaning they bloom in autumn or winter. Scientists call these short-day plants. Others flower only when nights are short, blooming in spring and summer. These are long-day plants, and some plants don't care about day length at all. They bloom whenever conditions feel right. Scientists call those day-neutral plants. The mechanism inside the plant is remarkable. Plants contain a light-sensitive protein called phytochrome. This protein changes its shape depending on whether it has been exposed to light or darkness. During the night, it slowly shifts into one form. When light hits it, it shifts back. By measuring how far along that shift has gone, the plant can sense how long the night lasted. It's a biological clock built from chemistry, running silently inside every leaf. This discovery helped explain something farmers had noticed for centuries without being able to explain. Why moving a plant to a different latitude, a different place on Earth, could completely disrupt its blooming cycle. A plant bred in the short days of northern winters might never flower if you grew it near the equator, where days and nights stay nearly equal all year long. The tilt of the earth doesn't just shape the seasons we feel. It shapes the invisible rhythms inside living things. Every flowering plant on this planet has tuned itself over millions of years to the slow lean of this world as it travels around the sun. Garner and Allard found the key to understanding that. But the plants had been reading that signal all along, long before any human thought to ask the question. Quietly, patiently, the way plants do everything. Most people think the seasons are simple. Earth tilts. One side gets more sun. That side gets hot. The other side gets cold. But the ocean quietly rewrites that story every single year, and most of us never notice. Here is something that surprises almost everyone. The ocean does not heat up and cool down the way land does. Water holds heat for a very long time. Rock and soil lose heat quickly. This difference has a name. Scientists call it heat capacity, which means how much energy a material can store before its temperature changes. Water's heat capacity is enormous. It takes nearly 5 times more energy to warm a bucket of water than to warm the same amount of dry soil by the same amount. That gap changes everything about how seasons feel. Coastal cities feel this every day. A city sitting right on the ocean shore will have mild summers and mild winters. A city deep inland, far from any large body of water, will bake in summer and freeze in winter. The ocean acts like a giant cushion, absorbing heat slowly in summer and releasing it slowly in winter. It smooths out the sharp edges of the seasons. Without it, the temperature swings across the year would be far more violent than anything most of us have ever felt. The Pacific Ocean off the coast of Western Europe does something remarkable. It carries warm water all the way from near the tropics up toward the north. In a slow river of heat called the Gulf Stream. This current keeps countries like the United Kingdom and Norway far warmer than they should be for their latitude, their position on the globe. Cities at the same latitude in Canada sit buried under deep snow for months. London rarely sees that kind of cold. The ocean is carrying warmth to places the sun alone would leave frozen. Now here is the part that feels almost impossible. Earth is actually closest to the sun in January, not July. January. Earth's orbit is not a perfect circle. It's a slight oval, and the point where Earth swings nearest to the sun happens in early winter for the northern hemisphere. Scientists call this the perihelion, which simply means the closest point in the orbit. Earth is about 3 million miles closer to the sun in January than it is in July. And yet, the northern hemisphere is cold. The tilt matters far more than the distance. But the ocean makes this even stranger. Because Earth is closer to the sun in January, it actually receives slightly more total solar energy during northern hemisphere winter. The southern hemisphere has its summer during this time, and that summer is technically a little more intense than the northern hemisphere's summer in July. But the southern hemisphere is covered mostly by ocean. All that extra solar energy gets absorbed by water, stored quietly, and released slowly. The ocean swallows the difference and evens things out. The two hemispheres end up feeling more similar than the raw numbers would suggest. The ocean also delays the seasons in a way that catches people off guard. The hottest days of summer in a coastal region don't arrive right at the summer solstice in late June. They arrive weeks later, often in August. The ocean is still absorbing heat, still warming up, long after the days have started getting shorter. The same thing happens in rivers. The coldest days of winter don't arrive right at the December solstice. They come in January or February, after the ocean has finally given up the last of its stored warmth. Scientists call this the lag of the seasons, and the ocean is the reason it exists. There is something deeply calming about this. The ocean is patient in a way that nothing else on Earth quite matches. It takes its time warming. It takes its time cooling. While the land snaps quickly from one extreme to the next, the ocean moves slowly, steadily, like something that has been doing this for so long that it no longer needs to hurry. The sea covers more than 70% of Earth's surface. It is the largest single force shaping how the seasons actually feel to every living thing on this planet. The tilt of Earth sets the rhythm, but the ocean decides the volume. It turns what could be a harsh, lurching swing between extremes into something gentler, something livable. The seasons arrive, and the ocean is already there, waiting, ready to soften the edges and hold the warmth a little longer than the calendar says it should. Everything connects. The tilt of a spinning planet, the slow memory of deep water, the warmth carried north by invisible currents. All of it working together quietly while the world sleeps. The seasons don't just change the temperature. They set the whole atmosphere in motion. Every year, as Earth tilts toward and away from the sun, the air above our planet shifts with it. Warm air rises near the equator, where sunlight hits most directly. Cool air sinks near the poles. This constant movement creates the great wind belts that circle our planet, the trade winds, the westerlies, the polar easterlies. These winds have carried sailors across oceans for thousands of years. They still guide every storm, every cloud, every breath of breeze you feel on your face. The tilt drives all of it. In summer, the land heats up faster than the ocean. The warm air above the land rises quickly, and cooler ocean air rushes in to fill the space. This is how sea breezes form along coastlines in summer. The ocean breathing cool air onto the shore. In winter, the pattern reverses. The land cools faster than the sea, and warmer ocean air drifts inland. The ocean acts like a slow, steady heartbeat beneath the seasons, always pushing and pulling the air around it. This exchange between land and sea creates something remarkable: the monsoon. In South Asia, the summer sun heats the vast land mass of the continent. Hot air rises in great columns above India and Southeast Asia. The Indian Ocean sends enormous walls of moist air rushing in to replace it. Those moisture-heavy winds rise, cool, and release their water as rain, sometimes for months at a time. Nearly 2 billion people depend on this seasonal rain to grow their food. The tilt of Earth, working through wind and ocean, feeds a quarter of the human race. Jet streams are another gift of the tilt. These are fast-moving rivers of air high in the atmosphere, flowing from west to east around the planet. They form where cold polar air meets warmer air from lower latitudes. In winter, when the temperature difference between the poles and the tropics is greatest, the jet streams grow stronger and push farther south. They steer storms. They shape weather patterns across entire continents. A dip in the jet stream can drag Arctic cold deep into places that rarely see snow. A ridge in it can hold heat over a region for weeks. The seasons even shape the chemistry of the air itself. In spring and summer, plants across the northern hemisphere absorb enormous amounts of carbon dioxide as they grow. Scientists measuring carbon dioxide levels in the atmosphere can actually see this happen. The numbers dip slightly every northern hemisphere spring, then rise again in autumn as leaves fall and decay releases that carbon back. Earth is breathing. The tilt of its axis sets the rhythm of each breath. Rainfall follows the seasons too, and not just through monsoons. The great rain belts of the tropics shift north and south with the sun throughout the year. In the wet season, towering thunderstorms build over the Amazon, the Congo Basin, and the forests of Southeast Asia. In the dry season, those same forests wait in silence for the rains to return. The timing of these rains determines which trees grow, which rivers run full, which animals breed. Everything downstream of the sky depends on when the seasons arrive. Even the ocean's surface temperature shifts with the seasons. The top layer of the sea warms in summer and cools in winter. And this warming and cooling affects the storms that form above it. Hurricanes and typhoons need warm ocean water to build their power. They form most often in late summer and early autumn, when the ocean surface has had months of sunlight to warm it. The tilt of Earth, by controlling when and how much sunlight reaches the sea, controls when the great storms are born. Snow and ice play their own part in this system. Fresh snow reflects sunlight back into space instead of absorbing it. In winter, when snow covers vast stretches of land, less solar energy stays near the surface. This helps keep temperatures cold. In spring, as snow melts and dark ground appears, more sunlight is absorbed, warming the land faster. The seasons help regulate themselves through this feedback, a quiet balancing act written in ice and light. All of these systems, wind, rain, jet streams, ocean heat, snow cover, are connected to a single elegant fact. Earth is tilted 23.5 degrees. That lean, held steady through the year, sets every one of these forces in motion. The monsoon rains, the trade winds, the hurricane season, the breath of the forests. They are all responses to the same slow turning of a tilted world around its star. Everything answers to the tilt. Earth is not the only world that tilts. Every planet in our solar system leans at its own angle. And that lean, or the lack of it, changes everything about how a world experiences its year. Mars tilts at about 25 degrees. That's close to Earth's own tilt of 23.5 degrees. Because of this, Mars has 4 seasons, just like we do. Spring, summer, autumn, winter. They all come to Mars in their turn. But Mars takes nearly 2 Earth years to circle the Sun. So each Martian season lasts roughly 6 of our months. A summer on Mars stretches on, long and cold and thin-aired, beneath a pale butterscotch sky. And yet, even with seasons that mirror our own, Mars feels nothing like home. Its atmosphere is very thin, barely a wisp compared to Earth's. That thin air can't hold heat the way ours does. So even in Martian summer, temperatures near the equator might reach a mild 70 degrees Fahrenheit at midday, then plunge to -100 at night. The seasons are real, but the warmth is fragile, and the cold is always close. Mars also has something Earth does not. Its orbit around the Sun is more oval-shaped, more stretched out. Scientists call this an eccentric orbit, one that swings closer to the Sun at some points and farther away at others. Because of this, Martian summers in the southern half of the planet are shorter and hotter, while winters there are longer and colder. The northern half gets the opposite. The shape of the orbit adds a second layer of change on top of the tilt. Now consider Uranus. This distant, pale blue planet doesn't just tilt a little. It tilts at 98 degrees. That means Uranus is essentially rolling on its side as it moves through space. Its north pole points almost directly at the sun for part of its year. Then, as Uranus continues its slow orbit, that same pole swings away into total darkness. One pole bakes in sunlight for 42 Earth years. Then it sits in cold, unbroken night for another 42 years. The other pole does the same, just in reverse. The seasons on Uranus are not gentle shifts. They are long, extreme, and almost hard to imagine. Scientists still debate exactly why Uranus tilts so far. The leading idea is that a very large object, perhaps a planet-sized body, struck Uranus long ago and knocked it sideways. That ancient collision, billions of years back, still shapes every season on that world today. One moment of violence echoing forward across all of time. Saturn tilts at about 27 degrees, slightly more than Earth. It has seasons too, though a full Saturnian year takes about 29 Earth years to complete. Each season on Saturn lasts roughly 7 of our years. During Saturn's summer, scientists have watched its northern hemisphere glow, a faint golden hue, warmed just slightly more by the distant sun. The rings cast long shadows across the planet's face as the angle of sunlight shifts. Even from billions of miles away, the tilt of a world writes itself across its surface. Venus, by contrast, barely tilts at all. Its axial tilt is only about 3 degrees. With almost no lean, Venus has almost no seasons. The sun strikes its surface at nearly the same angle all year long. But Venus has its own strangeness. It rotates so slowly and in the opposite direction from most planets that a single day on Venus is longer than its entire year. The sun rises in the west and sets in the east. Seasons, as we know them, simply don't exist there. The heat is constant, crushing, and everywhere. Mercury has almost no tilt either, just 0.03 degrees. But because Mercury orbits so close to the sun and has no real atmosphere to spread heat around, temperatures swing wildly between day and night. The side facing the sun can reach 800 degrees Fahrenheit. The side in shadow drops to minus 290. Not seasons in the way we know them, just the raw, unfiltered power of distance and exposure. What all of this shows is that tilt is not a small detail. It is one of the great shapers of a world. A few degrees more, a few degrees less, and everything changes. The length of the days, the depth of the cold, the reach of the warmth. Earth's tilt of 23.5 degrees sits in a kind of quiet middle ground, steady enough to give us 4 true seasons, gentle enough to let life thrive through all of them. We are tilted just right. And that, in the long story of planets and orbits and ancient collisions, is a rare and quiet gift. Long before anyone wrote down a single word, people watched the sky. They noticed things. They kept track. The sun rose a little farther north each morning through spring. It climbed higher at noon in summer. Then slowly, quietly, it began to pull back south again. These patterns were not random. They were a clock, and ancient people learned to read it. Thousands of years ago, builders at Stonehenge in southern England arranged massive stones in a careful circle. Some of those stones weigh as much as 25 tons. They were dragged from quarries miles away, and they were placed with extraordinary care, aligned so that on the morning of the summer solstice, the sun rises in perfect line with the central altar stone. The light comes in like a slow golden arrow. It was not an accident. It was a calendar built in stone. Stonehenge is roughly 5,000 years old. The people who built it had no telescopes. They had no written math, but they understood the sun's path across the sky with stunning precision. They knew that the solstice marked the longest day of the year. They knew the seasons turned on that moment. They built their greatest monument to honor it. Across the Atlantic Ocean, the ancient Maya civilization tracked the sun with equal care. Their pyramids were built to catch specific angles of light at specific times of year. At the Pyramid of El Castillo in Mexico, something remarkable happens every spring and fall equinox. As the afternoon sun moves lower in the sky, the shadows on the pyramid steps create the shape of a serpent crawling down the stone. The effect lasts only a few minutes. It was designed that way on purpose thousands of years ago. The light itself was the message. The Maya calendar was one of the most precise ever made by any ancient culture. They tracked the solar year to within a fraction of a day. They did this by watching where the sun set on the horizon, night after night, season after season. They used the light as their instrument. In ancient Egypt, temples were built to align with the rising sun on particular mornings. The great temple of Abu Simbel was carved directly into a cliff face. Twice a year, on specific dates, the rising sun shines through the entrance and travels deep into the temple's inner chamber. It lights up the carved faces of the gods inside. This happens on the anniversary of the pharaoh Ramesses II's birth and coronation. The Egyptians engineered the light to fall exactly where they wanted it, on exactly the right days. These were not coincidences. They were acts of deep observation. Generations of people watched the sun move across the sky and recorded what they saw. They noticed that the sun's angle changed with the seasons. They noticed that the light fell differently in summer than in winter. The shadows were longer in December. The noon sun was higher in June. They built their understanding of the seasons into the very stones they raised. In Ireland, a monument called Newgrange is even older than Stonehenge. It was built more than 5,000 years ago, making it older than the Egyptian pyramids. Newgrange is a large circular mound with a long inner passage. On the morning of the winter solstice, the shortest day of the year, a narrow beam of sunlight enters through a small opening above the doorway. It travels 19 meters down the dark passage and lights up the inner chamber for about 17 minutes. Then the light fades. It happens once a year. The builders aligned the whole structure to catch that single beam of winter light. Think about what that means. The people who built Newgrange lived in a world without clocks, without calendars, without written records, and yet they understood the geometry of the sun's path so well that they could aim a beam of light down a stone corridor and hit a target the size of a room. 5,000 years into the future, the light still arrives, right on schedule. These ancient Skywatchers understood something that took modern science centuries to explain in full. Earth's tilt causes the sun to trace a different path across the sky in each season. The sun rises and sets at different points on the horizon. Its noon position changes. The length of its arc through the sky changes, and the angle at which its light strikes the ground changes. All of that variation is written in light. The ancients read it with their eyes and their patience and their stones. The sky was their textbook. The sun was their teacher. And the seasons were the lesson that never stopped repeating. There is a sound that comes with the seasons. It isn't one sound. It's thousands, layered over each other across centuries of human life. Listen to the earliest farmers. Around 10,000 years ago, people in the Fertile Crescent, that curved stretch of rich land across what is now Iraq, Syria, and Turkey, began to plant crops in rhythm with the sun. They watched the angle of light change. They felt the soil warm, and when the days grew long enough, they pressed seeds into the ground. The sound of that first deliberate planting was the sound of civilization beginning. Seasons didn't just shape when people farmed. They shaped everything. The great river floods of ancient Egypt came like clockwork every summer. The Nile swelled with water from distant rains far to the south in Ethiopia. When it pulled back, it left behind a thick layer of dark, rich silt, the kind of soil that almost grows food on its own. Egyptian farmers built their entire calendar around this flood. Their year had 3 seasons: the flood, the planting, and the harvest. Not 4, 3, because that's what the land gave them. Every ancient culture heard the seasons differently. In northern Europe, the long, dark winters were something to survive. People stored food, stayed close to fire, and waited. The return of longer days in spring was not a quiet event. It was celebrated loudly, with festivals and feasts. Many of those celebrations still echo in the holidays we keep today. The tilt of Earth didn't just feed people, it moved them. For thousands of years, human groups followed the seasons across the land. They were pastoralists, people who raised animals and moved with the grass. When summer dried the lowland pastures, they climbed into cooler highlands. When winter came, they descended again. This seasonal migration, called transhumance, still happens in parts of the Alps, the Himalayas, and the mountains of Central Asia. The sound of it is the sound of bells on goats and boots on stone paths worn smooth by 10,000 years of walking. Seasons shaped the sound of war, too. Ancient armies almost never fought in winter. The ground was too hard. The roads were mud. Supplies couldn't move. Campaigns began in spring and ended before the first frost. Julius Caesar planned his invasions around the season. Napoleon's march into Russia in 1812 failed partly because he misjudged the speed of the Russian winter. The cold came early. His army, stretched thin across a frozen land, collapsed. Even the great trading routes of history moved with the seasons. The monsoon winds of the Indian Ocean, those massive seasonal shifts in wind direction, driven by the heating and cooling of land and sea, carried merchants from Arabia to India and back again for over 2,000 years. Sailors didn't fight these winds. They read them. They waited for the right season, then let the wind carry them. The spice trade, the silk trade, the spread of religions and languages across the ancient world. All of it moved on seasonal winds. The seasons shaped music, too. Many of the world's oldest musical traditions are tied to planting and harvest. Drum beats that called communities together for the sowing season. Songs sung during harvest to keep workers moving in rhythm. Even the classical music of Europe carries echoes of this. Antonio Vivaldi wrote his famous set of violin pieces called The Four Seasons in the early 1700s. Each piece tries to capture a season in sound: the warmth of summer, the chill of winter, the softness of spring. People have been listening to those pieces for 300 years. There is something deeper here than just farming or music or war. The tilt of Earth created a world that changes, and a world that changes demands that the creatures living in it pay attention. Humans paid attention. They built calendars. They raised stone monuments to mark the solstice. They invented writing in part to keep track of planting seasons and flood cycles. The need to understand the seasons pushed human minds forward. Some scientists believe the very concept of time, the way humans think about past and future, about planning and memory, grew partly from living in a world with seasons, a creature that lives in a place where conditions never change, doesn't need to think ahead. But a creature that knows winter is coming learns to prepare. It learns to imagine a future. That imagination, some researchers suggest, is one of the roots of human thought itself. The tilt of Earth is just 23.5 degrees. But from that small lean, all of this grew. There is a kind of math that doesn't feel like math at all. It feels more like music. Slow, patient, repeating patterns that stretch across thousands of years. Earth moves through space in ways that follow very precise rules. And those rules, working together, have shaped every ice age, every warm period, every great shift in climate that this planet has ever known. In the early 20th century, a Serbian scientist named Milankovitch spent years doing something remarkable. He sat down and calculated by hand exactly how Earth's position in space changes over long stretches of time. He wasn't looking at seasons that last a few months. He was tracking cycles that take tens of thousands of years to complete. What he found was that Earth doesn't move through space in a simple, steady way. It wobbles, it tilts, it drifts, and all of that motion follows elegant, predictable patterns. The first pattern is the shape of Earth's orbit around the Sun. Earth doesn't travel in a perfect circle. It travels in an ellipse, which is a slightly stretched oval. But that oval shape changes slowly over time. Sometimes the orbit is nearly circular. Sometimes it stretches a little longer. This cycle takes about 100,000 years to complete. When the orbit is more stretched, Earth spends more time farther from the Sun during part of the year. That changes how much solar energy the planet receives. Scientists call this change in orbital shape eccentricity. The second pattern involves the tilt of Earth's axis. Right now, Earth tilts at about 23.5 degrees, but that angle isn't fixed forever. Over roughly 41,000 years, the tilt slowly shifts between about 22 degrees and 24.5 degrees. When the tilt is greater, seasons become more extreme. Summers grow hotter. Winters grow colder. When the tilt decreases, seasons become milder. The difference seems small, but across thousands of years, Even a small change in tilt reshapes the entire climate of the planet. The third pattern is called precession. This is the slow wobble of Earth's axis itself, like the wobble of a spinning top that's starting to slow down. Earth's axis traces a slow circle in space, completing one full wobble roughly every 26,000 years. Precession changes which part of Earth's orbit falls during which season. Right now, Earth is slightly closer to the Sun during the Northern Hemisphere's winter. About 13,000 years from now, that will be reversed. The Northern Hemisphere will be closer to the Sun in summer, making summers there more intense. These three cycles don't work alone. They overlap. They combine. Sometimes they push in the same direction, and the effect on climate is strong. Sometimes they pull against each other, and the effect is muted. Milankovitch understood that it was the combination of all three that drove the great ice ages. When the cycles lined up in a way that reduced sunlight reaching the high northern latitudes during summer, ice could grow. Snow that didn't melt in summer would build up year after year. Glaciers would spread. The planet would cool. The numbers Milankovitch calculated by hand have since been confirmed by modern computers and by evidence pulled from deep inside the Earth itself. Scientists drill into ancient ice in Antarctica and Greenland, pulling out cores that hold tiny bubbles of air trapped thousands of years ago. Those bubbles carry a record of past temperatures and carbon dioxide levels. The record matches the cycles Milankovitch predicted. The math works. The universe, it turns out, keeps very careful records. What makes this beautiful is the scale of it. These cycles operate on timescales so vast that no single human life, no single civilization could ever watch one complete. The 41,000-year tilt cycle began before modern humans existed. The 100,000-year orbital cycle stretches back before our species had even evolved, and yet the patterns were always there, quietly running, shaping the ice and the warmth and the seasons that all life on Earth has ever known. Milankovitch gave us a way to see time differently, not as a straight line moving forward, but as a set of slow, overlapping waves. Each wave has its own rhythm. Each one influences the others. Together, they create something far more complex than any single cycle could produce alone. The climate of Earth isn't random. It follows rules. Deep, patient, mathematical rules written into the geometry of the solar system itself. The tilt of a planet, the shape of an orbit, the slow nod of an axis through space. These are the quiet forces that have governed ice ages and warm ages for hundreds of millions of years. Simple numbers, enormous consequences. The universe, as always, doing extraordinary things with very simple tools. There is a kind of quiet miracle in the fact that seasons happen at all. Earth sits at just the right distance from the sun, not so close that water boils away, not so far that it freezes solid and stays that way. Scientists call this the habitable zone, the narrow band around a star where liquid water can exist on a planet's surface. Earth lives right in the middle of it, and that position, combined with the 23.5-degree tilt, gives us the seasons we know. But the system is more fragile than it looks. The tilt itself is held steady by the moon. Our moon is unusually large for a planet our size. That mass acts like a kind of anchor, keeping Earth's tilt from wobbling too wildly over short periods of time. Without the moon, scientists believe Earth's axial tilt could swing dramatically over thousands of years, from nearly upright to deeply tilted and back again. The seasons would become something unrecognizable. Summers might scorch regions that are now mild. Winters might bury continents under ice that never fully melts. The moon, in other words, is part of why seasons are stable enough to support life. Now, even with that stability, the seasons are shifting. Not dramatically, not all at once, but measurably. Spring is arriving earlier in many parts of the world. Autumn is staying warmer longer. The timing of the seasons, as measured by temperature and the behavior of living things, has drifted from where it was just a century ago. Scientists track this in careful detail. They look at when flowers first bloom each year, when migratory birds arrive, when rivers fed by snowmelt begin to rise. These are called phenological records, which means records of how nature times itself across the calendar. those records show a clear pattern. The biological calendar is shifting. The seasons are not arriving when they used to. The cause is the warming of Earth's lower atmosphere, the thin layer of gas that wraps our planet, mostly nitrogen and oxygen, with small amounts of carbon dioxide and water vapor, traps heat from the sun. This is the greenhouse effect, and it is not a new idea. Scientists have understood it since the 1800s. In the right amount, it keeps Earth warm enough for life. Without it, the average surface temperature would be around -18 degrees Celsius, well below freezing. The greenhouse effect is why Earth is not a frozen rock. But when more heat-trapping gases build up in the atmosphere, more heat stays near the surface. And that extra warmth is enough to nudge the seasons, not to break them, but to bend them. The Arctic feels this most strongly. The far north is warming roughly 4 times faster than the rest of the planet. Sea ice, which once covered vast stretches of the Arctic Ocean through summer, now retreats earlier each year. The white ice that used to reflect sunlight back into space is being replaced by dark open water, which absorbs heat instead. That absorbed heat warms the region further. Scientists call this the ice albedo feedback, where the loss of reflective ice causes more warming, which causes more ice loss. It is a loop, and loops, once started, are hard to slow. The seasons are also shifting in ways that disconnect living systems from each other. A flower that blooms 2 weeks earlier may open before the insect that pollinates it has emerged. A bird that arrives on its ancient schedule may find the insects it depends on have already peaked and gone. These mismatches, small on their own, ripple outward through ecosystems in ways that are still being studied. Everything in nature is timed to everything else. The seasons are the clock. When the clock drifts, the whole system feels it, and yet the underlying engine keeps running. Earth still tilts. It still orbits the sun. The solstices and equinoxes still arrive on schedule, governed by orbital mechanics that no amount of surface warming can change. The astronomical seasons, defined by Earth's position in space, remain precise. It is the biological and climatic seasons the lived experience of warmth and cold, of bloom and frost, that are slowly moving out of step with those ancient markers. This is what makes the system feel so delicate. The astronomy is fixed. The tilt is steady. The orbit is reliable. But the thin skin of air and water and life that sits on top of all that geometry is sensitive to small changes in ways that the numbers alone don't fully capture. The miracle is not just that the system works. The miracle is how many things have to stay in balance for it to keep working. The atmosphere is thin. From space, it looks like a faint blue glow clinging to the edge of our planet. And yet this thin shell of air does something remarkable. It takes the heat that Earth receives from the sun and spreads it around. It carries the seasons from place to place like a slow, breathing current. We understand a great deal about how this works, but scientists will tell you honestly that the atmosphere still holds surprises. There are questions that remain open. There are patterns that don't quite fit the models. And that's not a failure of science. That's science doing exactly what it's supposed to do, noticing what it doesn't yet know. One of the biggest open questions involves something called the jet stream. The jet stream is a fast river of wind that flows high in the atmosphere, roughly 6 to 9 miles above the ground. It circles the planet in a wavy, winding path. It steers storms. It shapes winters. It helps determine whether a season feels mild or brutal in any given year. Scientists know the jet stream exists and can track it in real time. What they're still working to understand is exactly how it will change as the planet warms. Some evidence suggests the jet stream is slowing down and becoming more wavy. This could trap cold air in some regions for longer stretches and push warm air into places that rarely see it. But the picture isn't fully clear yet. The research is ongoing, and the data is still coming in. The atmosphere also plays a role in something called the polar vortex. The polar vortex is a large area of cold, spinning air that sits over the Arctic during winter. Most of the time, it stays where it belongs, locked near the poles. But sometimes it weakens and wobbles. When it does, blasts of Arctic air spill southward into places like North America and Europe. Cities that rarely see deep cold can suddenly find themselves buried in it. Scientists understand the basic mechanics of this. What they're still studying is why the polar vortex weakens when it does, and whether those disruptions are becoming more frequent. The atmosphere, it turns out, is harder to predict than it looks. There's another mystery tied to something called atmospheric rivers. These are long, narrow bands of moisture that flow through the sky, sometimes stretching thousands of miles. They carry enormous amounts of water vapor from the tropics toward the poles. When they make landfall, they can bring heavy rain or snow, sometimes flooding entire regions in a matter of days. California, for example, gets a large portion of its winter rainfall from just a handful of these events each year. Scientists can see them forming and track them as they move. But predicting exactly where they'll hit and how strong they'll be remains one of the harder problems in weather science. The atmosphere moves in ways that are still teaching us things. Even the basic question of how the atmosphere transfers heat between the equator and the poles isn't fully solved. Scientists know that warm air rises near the equator and flows toward the poles, while cold air sinks and flows back. This general pattern has a name: the general circulation of the atmosphere. But the details of how this circulation shifts with the seasons and how it responds to changes in sea ice or land temperature are still being refined. Every new satellite, every new ocean buoy, every new weather station adds a little more to the picture. What makes all of this so striking is how connected it is. The atmosphere doesn't work alone. It talks to the ocean. It responds to the ice sheets. It reacts to forests and deserts and the slow breathing of the land. When one part of the system shifts, the atmosphere feels it. And when the atmosphere shifts, everything else feels that too. Scientists call this kind of linked behavior a feedback loop, where one change triggers another, which triggers another, rippling outward in ways that are hard to trace all the way to the end. There's something quietly wonderful about this. We've been watching the sky for thousands of years. We've built instruments of incredible precision. We've launched satellites that can measure the temperature of a single square mile of ocean from hundreds of miles up. And still, the atmosphere keeps offering new questions. It keeps showing us that the world is more intricate than we imagined. The seasons arrive each year with the same reliable rhythm, but the air that carries them, that wraps around the planet and breathes the warmth from place to place, is still revealing its secrets. Slowly, patiently, the way all the best things do. Deep in the ice of Antarctica, there are layers of frozen snow that have been building up for hundreds of thousands of years. Each layer holds tiny bubbles of ancient air. Scientists can drill down into that ice and pull out a core, a long cylinder of frozen time, and read those bubbles like pages in a book. They can measure the gases trapped inside. They can see what the atmosphere looked like long before any human was alive to breathe it. What those ice cores tell us is extraordinary. Earth has not always had the seasons we know today. The tilt, the orbit, the slow wobble of our planet through space. All of these things shift over enormous stretches of time. And when they shift, the seasons shift with them. Not in ways we'd notice in a single lifetime, but over thousands and millions of years, those small changes add up to something vast. Earth has passed through at least 5 major ice ages in its long history. The most recent one ended roughly 12,000 years ago. During that time, thick sheets of ice covered much of North America and Europe. The ice stretched down from the poles like a slow, grinding tide. Glaciers, those massive rivers of ice, carved out valleys, scraped away mountains, and left behind the lakes and hills we still see today. The Great Lakes of North America were shaped by glaciers. So were the fjords of Norway, those long, narrow inlets of sea carved deep into the rock by ancient ice. These ice ages were not random. They were driven, at least in part, by the same forces that shape our seasons today. The Serbian scientist Milankovitch spent decades calculating how small changes in Earth's orbit and tilt could cool the planet enough to let ice build up over centuries. His work, done mostly in the early 20th century, showed that ice ages follow a rhythm. They come and go on cycles of roughly 100,000 years, 41,000 years, and 23,000 years. Each cycle is tied to a different wobble in Earth's path through space. Right now, Earth is in a warm period between ice ages. Scientists call this an interglacial period, a pause in the long freeze. Based on the Milankovitch cycles, another ice age would likely begin tens of thousands of years from now. But the rise of greenhouse gases in the atmosphere has complicated that picture. Evidence suggests that human activity may have already delayed the next glacial period by pushing more heat into the climate system. The ancient rhythm of ice and warmth is still turning, but something new has entered the equation. Look far enough ahead, and the changes grow even more dramatic. Over the next few million years, the continents will continue to drift. Africa is slowly pushing into Europe. The Mediterranean Sea will eventually close. Australia is creeping northward toward Asia. As the continents move, they change how ocean currents flow and how heat spreads around the planet. That changes the seasons too. A world with different oceans and different land masses will have different patterns of warmth and cold, different monsoons, different winters. In about 500 million years, the sun will be roughly 10% brighter than it is today. That extra heat will slowly push Earth's climate toward conditions too warm for ice to form at the poles at all. The deep cold of winter will still come, driven by the tilt, but the planet's overall warmth will be higher. Seasons will still exist, but they'll exist on a warmer world. And in about 5 billion years, the sun will reach the end of its long life as a stable star. It will swell into a red giant, a star so large it may swallow the inner planets entirely. Earth, as we know, it will be gone. But the atoms that made up our oceans, our ice, our air, will not disappear. They'll scatter into space, carried outward by the dying star's last breath. Those atoms may one day drift into a new cloud of gas and dust. That cloud may collapse under its own gravity. A new star may ignite. New planets may form around it. And somewhere in that new solar system, on some rocky world at just the right distance from its star, there may be a slight tilt, a lean of a few degrees, inherited from the chaos of formation. And that tilt may cause one side of the planet to face its sun a little more directly in one part of the year, and a little less directly in another. Ice may build in the cold months. Flowers may open in the warm ones. The seasons are not just Earth's story. They are the universe's way of turning light into life, again and again. Across time we can barely imagine. Step all the way back for a moment, not just from the seasons themselves, but from the whole spinning, tilting, breathing world that makes them possible. Look at it from far above. What you see is not four separate things. What you see is one continuous motion, folding into itself over and over without end. The seasons are not four chapters in a book. They are one long sentence that never stops. Summer carries the seeds of autumn inside it. Autumn holds the quiet promise of winter. Winter is already dreaming of spring. And spring, with all its green urgency, is already reaching toward the heat of summer again. Each one flows into the next the way a river flows into the sea, without a seam, without a break. Think about what actually moves through these seasons. Water does. The same water that falls as snow in January melts into rivers in April. It rises into clouds in July. It returns as rain in October. That water has been cycling through this system for billions of years. Some of the water in tonight's rain may have once been locked inside a glacier during an ice age 10,000 years ago. The seasons are part of that ancient cycle, pulling water up and setting it down again and again. Carbon moves through the seasons too. In spring and summer, trees and grasses pull carbon dioxide out of the air and lock it inside their leaves and stems. Scientists can actually measure this. Every year, the amount of carbon dioxide in the atmosphere dips slightly during the northern hemisphere's summer because so much plant life is breathing it in. Then in autumn, when the leaves fall and decay, some of that carbon returns to the air. The whole planet inhales and exhales with the tilt of its axis. Animals carry the seasons inside their bodies. Birds that hatch in summer carry the memory of long days in the length of their wings and the timing of their songs. Salmon that swim upstream in autumn are following cues written into them over millions of years of seasonal change. Even the bacteria in the soil respond to the shift in temperature and light. Life at every scale is tuned to the turning year. And here is something quietly astonishing. The tilt that causes all of this, that 23.5-degree lean that gives us our seasons, is not an accident of Earth alone. Scientists believe it was set, at least in part, by a collision with a Mars-sized body early in Earth's history. The same collision that created the moon. So the moon, hanging in the sky tonight, is a distant cousin of the seasons. It shares the same violent origin. The tilt that brings you summer and winter was born in the same moment as the pale light falling through your window on a clear night. The moon also helps keep that tilt stable. Without the moon's gravitational pull, Earth's axis would wobble far more wildly over time, swinging between extreme angles. The seasons would become chaotic and unpredictable. Life, as we know, it might never have found its footing. The moon acts like a quiet anchor, holding the tilt steady, keeping the seasons gentle enough for life to trust them. Zoom out further still. Our sun is the engine of all of this. It fuses hydrogen into helium deep in its core, releasing energy that travels 93 million miles through empty space and arrives here as light and warmth. That energy, landing on a tilted planet, becomes the seasons. It becomes the green of spring and the gold of autumn. It becomes the long blue shadows of a winter afternoon and the thick, heavy heat of a July evening. All of that comes from a star burning quietly in the dark, and the atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe right now, were forged inside stars that lived and died long before our sun was born. When those ancient stars exploded, they scattered their elements into space. Over millions of years, that scattered material gathered into a new cloud, collapsed under its own gravity, and became our solar system, became our sun, became Earth, became you. So when you feel the warmth of a summer afternoon, or watch the first frost form on a window in November, you are not just experiencing a change in weather. You are feeling the echo of something that began long before this planet existed. The seasons are the universe expressing itself through a tilted, spinning world, through water and carbon and light, through every living thing that has ever felt the year turn. everything connects. Everything always has. And so we arrive here, at the quiet end of everything we've learned tonight. Think about what this small planet has done. It has leaned itself at just the right angle, 23.5 degrees, and held that lean steady across billions of years. That single tilt, that one small tip away from perfectly upright, gave us everything. It gave us spring rains and summer heat. It gave us the slow gold of autumn and the deep, still cold of winter. All of it from one gentle lean. The earth didn't have to be this way. It could have stood perfectly straight, with no tilt at all, and every place on the planet would feel the same temperature every single day of the year. No seasons, no change, no great migrations of birds crossing the sky, no flowers waiting underground for the right moment to push upward into the light. Just one long, unchanging sameness. But that's not what happened. Something struck the young Earth long ago. A collision so large it knocked our planet into its tilt and flung debris into space that slowly gathered into the moon. That ancient crash, violent and enormous, set the angle, and from that angle, everything followed. The moon steadies our tilt even now, keeping it from wobbling too wildly, holding the seasons in their rhythm the way a hand holds a spinning top. The sun plays its part too. It doesn't move, we do. The earth carries us around the sun in a slow, year-long loop. And as we travel, our tilted angle means different parts of the planet lean toward the light at different times. Summer is not about being closer to the sun. It's about facing it more directly, receiving its rays at a steeper angle, soaking in more warmth per square foot of ground. Winter is the turning away, the gentle withdrawal, and all of this happens without a sound. Right now, as you rest, the earth is moving. It spins at roughly 1,000 miles per hour at the equator, carrying you through the dark without you feeling a thing. It also travels around the sun at about 67,000 miles per hour, and you feel none of that either. The planet holds you so gently, so steadily, that all of this enormous motion feels like stillness. Somewhere on Earth right now, it is summer. The sun is hanging high and bright over long, warm afternoons. Children are running through sprinklers, Farmers are watching their fields grow tall and green. Somewhere else on the same planet, it is winter. Snow is settling over quiet forests. Rivers are slowing under thin sheets of ice. The same sun, the same tilt, two completely different worlds happening at the same moment on the same spinning rock. The oceans are moving too right now. Great slow rivers of warm and cold water are circling the globe, carrying heat from the tropics toward the poles, softening the edges of every season they touch. The atmosphere is breathing warm air rising, cool air sinking, winds carrying moisture from the sea to the land, feeding the clouds that will become tomorrow's rain. Every part of this system touches every other part. The tilt shapes the seasons. The seasons shape the winds. The winds shape the oceans. The oceans shape the weather. The weather shapes the land. The land shapes the life. And the life, every creature, every forest, every coral reef, every field of wheat, shapes the air we breathe. It is all one thing, moving together, leaning together, turning together in the dark. And you are part of it. You are made of atoms forged inside ancient stars. You breathe air that has cycled through the lungs of every creature that ever lived on this planet. The water in your body has been rain and river and ocean and cloud. You are not separate from this world. You are woven into it, the same way the seasons are woven into the tilt, the same way the tilt is woven into the spin, the same way the spin is woven into the long, slow orbit around a quiet star. The planet is turning right now, slowly, steadily, beautifully. The stars are out. The moon, if it's up tonight, is pulling gently at the oceans. Somewhere, a glacier is inching forward by a fraction of an inch. Somewhere, a seed is waiting in the cold ground for the first warmth of spring. Everything is in its place. Everything is moving at exactly the right speed. The universe is enormous, and you are small. And somehow, that is the most comforting thing in the world. Rest now. The earth has you. Subscribe for a brand new earth topic every night, one tap, and something wonderful is waiting for you tomorrow. Sweet dreams.